Alright, so we're going to go ahead and get started here, and we're continuing to talk about gravity. Our goals for today are to create a model that will help us kind of visualize what gravity looks like. We also want to kind of understand Newton's third law, which you come to my class kind of knowing, but specifically we want to talk about a special component of Newton's third law, which is called a third law pair, and define that and figure out how to use that. So that's kind of our goals for today. So let's just go ahead and remind ourselves what we decided in class, and that is that gravity is an attractive force between all masses. And a lot of times when we think about gravity, remember we think about big objects, but as we saw with the Cavendish experiment, gravity is existent in all pieces of matter. So I want to shrink our world of mass to the particle level. So think about the smallest piece of mass that you can imagine. Now a chemist might say that's something like the atom. So I'm just going to represent that with a dot with a circle around it. And this is just called a particle diagram. And it allows us to look at the individual particles, or masslets, I guess you could call them, in whatever we're analyzing. Alright, so here's where I'd like to begin. I'd like you to read this question and think about how you would answer it based on your understanding of physics so far. Okay, so we're going to come back to that question. Let's think a little bit about how these particle diagrams that we talked just earlier about can help us understand what is happening and how to make an accurate prediction of what the force of the water bottle would be on the car and vice versa. So here in front of me I have two different masses, and we'll just say that they each have one piece of mass inside them. So we could think of these as the smallest pieces of matter, so maybe each of them has one atom in. So if looking at the mass, we could say the mass of A is equal to 1 because there is one masslet. Okay. If we look at B, it also has one masslet, so we would say the mass of B is also equal to 1. Now the next thing we want to think about, well, what about the force of gravity? So force of gravity, we look at what is the attractive force between them. So we might represent that as a circle between the masslets. Therefore, we could say the force of G, force of gravity, on A by B, and we could represent this with a vector pointing from A to B, because B is attracting it, so the force of gravity is towards B. Okay, now if we were looking at B, we could say the force of gravity is also acting on B, but instead of on A, it's going to be on B by A. And we could represent that as a vector going in the opposite direction. So what can we say about these two forces? Well, each one was worth 1, so we could say that these two are equal to each other. All right, well, let's take something a little more complicated now. So let's say that this mass B over here has actually two masslets, and let's say that A still continues to just have one masslet. So if we look at the mass of A, again, we're looking at just one masslet, and the mass of B is 2, because we've got two particles now, okay? So let's go ahead and look at the force of gravity. So remember, the force of gravity is individual. So for each particle, each masslet exerts a force on the other masslet. So right here, these two particles are attracted to each other. So we can represent that as a circle. And that circle represents the attractive force between A and B for this particle of A to this particle of B. But what about this particle over here? It's also attracted to that particle. So we'll have to add another circle, because this particle in A is actually attracted to individually each particle in B. Okay, so what do we have here then if we analyze the force of A. So now we've got the force of gravity on A by B is equal to what? Well, there are two different vectors that B is sending out. So we could say that the force of gravity is equal to 2 in this case. But what about the force of gravity that A exerts? Well, again, it would be opposite, but there are two different vectors going from A to B, and they go in different directions. So again, we could say that that is equal to 2. So if we were to draw the vector, then we could represent that resultant vector equal and opposite. All right, so let's do one more example here. And let's say that this object A here is, let's just say it's a really big cat, and this cat is made of 4 gigantic particles because, of course, A is supposed to be a real object. I mean, we've been talking theoretically, but they're real objects. And let's say that B is a giant attack billy goat, like the one that lives at my house, and he is actually smaller than the cat, so he's only made of 3 particles. So what I'd like you to do is I'd like you to think back to the gravitational force and the relationship to the masslets on the previous 2 slides, and think about what is the relationship. How could we predict what is the gravitational force on the cat by the goat and the goat by the cat? And remember, we did that by making circles. So how many circles would we have to make to find the gravitational force for this? So you should, by looking back at the previous examples, you should see that the gravitational force between these 2 objects is going to be equal to 12. Okay? And we got that relationship because if you take the product of the masses, so m1 times m2, okay, you get the force of gravity. So if you take 4 for the cat times 3 for the crazy billy goat, you get 12. Therefore, we can say that f of g is proportional to the product of the masses. So we quantified on the last one the force of gravity between the goat and the cat, but remember that we got f of g was equal to 12. Okay, so remember that we can say that f of g on the cat by the goat, oops, that's not g, was equal to and opposite of the force of gravity on the goat by the cat. Okay, so this right here, this relationship that we see of equality between the 2 forces is actually what Newton was talking about when he talked about Newton's third law. So a lot of times, like we hear, Newton's third law is for every action there's an equal and opposite reaction. And personally, I think that's a little bit misleading because it indicates that you have motion always, okay, which you don't always have motion in forces, all right? So the third law pair is really what Newton was talking about when he was talking about his third law, and that is it's a pair of forces that are equal in magnitude and opposite in direction. So in the case of the gravitational force between the cat and the goat, that third law pair would be seen as this one that we have down below. And if we were to draw what that third law pair looked like, we would just have these 2 vectors, and of course they'd be fully labeled, would represent the third law pair. All right, so now we are back at our question, and I'll just have you read this for a second and think about now, given what we've talked about with gravity, what is the gravitational force on the truck and the water bottle? And you should know that the answer is they are equal because they are a third law pair. And I'll give you a second here just to think about what the gravitational force of the Earth attracted to the person is. Okay, and again, the answer is 800 newtons. Okay, so the gravitational force of gravity that the person exerts on the Earth is also 800 because it's a third law pair, equal and opposite. All right, well, up until this point, we've really only talked about how the mass of the objects affects the force of gravity. And if we want to more accurately represent that, we need to take into consideration the distance between the two masses. And conceptually, everybody came to class pretty much knowing that as you move the objects further away from each other, the force of gravity decreases. So how does this mathematically then fit into an equation? And what we find, it's a little bit hard to visualize, but you can kind of think about if you took a flashlight and you were shining it at a wall. All right, well, let's say that this flashlight makes an image over here on the right, and the distance between the flashlight and the image is 1, okay? Now let's go ahead and say that the image in this case, so the distance between these two, the radius is going to be 1, and the screen over here, the size of the screen represents the force of gravity. So we'll just say that this is also 1. Okay, so the radius is 1 and the gravity is 1. Okay, so now we're going to go ahead and we're going to pick up this flashlight though, and we're going to move this guy back. We're going to double his radius. So now the radius, okay, is now twice that. All right. So what happens to the force of gravity is that that original image that we had here, that was our force of gravity, actually gets stretched out. So now it gets larger, okay? And you might ask, well, how much larger does it get? And actually what we see is that gravity gets spread out, so it gets weaker over that area, and gets spread out according to the square. All right, so the final equation for the force of gravity is right here in front of you, and that is the product of the masses divided by the radius squared. Okay, well, we just discussed in the last one the formula for gravity, so here are some examples, 1, 2, 3, and 4. And what I'd like you to do is compare the force of gravity and how it compares to the force of gravity on the other object. And in each of these blanks right here, I'd like you to think about, is it equal to, less than, or greater than? So you'll need to push pause and do a little practice there. All right, so you should have discovered that the first one was equal. This force was greater on number 2, this was greater on 3, and this one was greater on 4. All right, I'd like you to push pause, and I'd like you to read this question and think about how you would answer the question at the bottom, question A there. How would you expect the gravitational force to change? All right, so I hope you've thought about your answer, and I'd like you to think about the answer, which is there would be no change in that case. So I'd like you to think about why that is and reflect on why that is. Okay, that wraps it up. So just a reminder, remember our goals were to come up with a particle model that we could visualize gravity, and we've done that by saying we would connect the masslets with some sort of circle, and that circle represents f of g, which is different than the particle, which represents mass. Okay. The second thing we talked about was the third law pair. So remember, that's the equal and opposite force that we see with all interactions. So if you're sitting there on a chair, there is a third law pair. So any place that a physicist sees a force, they also see a third law pair. Okay, so that's one of the things we want to do to change our mindset into a physics mindset. And then finally, we've got this fancy equation down here, f of g equals g, which is a fancy constant you do not need to know because you can look it up on Wikipedia. But you do need to understand that the relationship between mass and gravity is a product, and the distance is a square, or the inverse square relationship. So as they get further away, okay, the gravitational force, gets bigger and bigger and bigger more rapidly. All right, good luck.